Hello learners. Let me ask you something simple. When you and your friend compare your test scores, do you usually calculate the average? That's your arithmetic mean at work. And when scientists measure growth rates, they often use another average called the geometric mean. So, let's define them properly. For two positive numbers a and b, the arithmetic mean a is bracket opener plus b bracket close divided by 2. The geometric mean g is the square root of a times b. Both a and g give us a central value, but they represent balance in different ways, one by addition, the other by multiplication. Isn't that fascinating? Now comes the big question. How do a and g compare? Let's compute a minus g, that is bracket opener plus b bracket close divided by 2 minus square root of ab. Simplify. We get bracket opener plus b minus to square root of ab bracket close divided by 2. But that numerator is actually bracket open square root of a minus square root of b close square, which is always greater than or equal to 0. So, the final result is a minus g equals bracket open square root a minus square root b close square divided by 2, which is greater than or equal to 0. That means arithmetic mean is always greater than or equal to geometric mean. Equality holds only when a equals b. That's the famous A.M.G.M inequality. Let's check this with numbers. Suppose a equals 9 and b equals 16. Arithmetic mean a is bracket open 9 plus 16 bracket close divided by 2, which equals 25 divided by 2, that is 12.5. Geometric mean g is square root of 9 times 16, which is square root of 144, equal to 12. See, a equals 12.5, g equals 12, and indeed a is greater than g. The difference shows up because the two numbers 9 and 16 are not equal. So whenever numbers are unequal, a beats g by a small margin. Why is this inequality so important? It tells us that averaging by addition is never less than averaging by multiplication. This principle is used in optimization problems, like minimizing cost, maximizing efficiency, or even distributing resources fairly. In higher mathematics and competitive exams, you'll often see the A.M.G.M inequality appear in algebraic inequalities, especially when finding minimum values of expressions. It's one of those golden tools you can always rely on, simple but powerful. Now let's solve a proper exam-style question. We are told the arithmetic mean of two positive numbers is 10 and the geometric mean is 8. We need to find the numbers. Step 1. From a equals 10, we have a plus b divided by 2 equals 10. Multiply both sides by 2. We get a plus b equals 20. Step 2. From g equals 8, we have square root of ab equals 8, which gives ab equals 64. Step 3. Use the identity bracket a minus b close square equals bracket a plus b close square minus 4ab. Substituting, we get 400 minus 256 equals 144. So, a minus b equals plus or minus 12. Step 4. Solve the system. With a plus b equals 20 and a minus b equals 12, we get a equals 16, b equals 4. If a minus b equals negative 12, we get a equals 4, b equals 16. So, the two numbers are 16 and 4, or 4 and 16. Done. Notice how both numbers are determined directly from a and g, unique up to order. Let's recap quickly. For two positive numbers a and b, arithmetic mean is bracket a plus b bracket divided by 2, and geometric mean is square root of ab. We proved that a is always greater than or equal to g, with equality only if a equals b. We checked a numerical example, explored why the inequality matters, and solved a problem where a and g determine the numbers themselves. That's the power of the A.M.G.M relationship. A simple formula, but a cornerstone of inequalities, optimization, and algebra. And in our next video, we'll explore more special series and their summation tricks. So stay tuned and remember, in the battle of means, A always stays on top of G unless the numbers are twins.